In this video, I'm going to show you how to solve rational inequalities using the sign table. In particular, we're going to consider the case where the right-hand side is 0. So here we want to solve this rational inequality. 2x minus 3 over x plus 3 is less than or equal to 0 on the real numbers. The way we do this is going to be very similar to the way we solve polynomial inequalities using a sign table. To use a sign table on a polynomial inequality, we started out by finding the roots of the left-hand side here. And we're going to do a similar thing here. Let's first find the roots of the left-hand side of this rational expression. So roots are just where the numerator is 0. So that's when this 2x minus 3 equals 0. If 2x minus 3 equals 0, then just add 3 to both sides, divide by 2, and you get x equals 3 halves. Okay. But now we're also going to consider the roots of the denominator as well, and those make the rational expression undefined, but they are important to put on our number line here. So why don't we go ahead and find that? So that's where x plus 3 equals 0. So x would equal negative 3. And now we've got these two roots here. This is really a root of the expression. This makes the expression undefined, but we'll put both of them on our number line. Put negative 3 and 3 halves. Now our number line can be partitioned into several intervals. There's negative infinity to negative 3. There's also negative 3 to 3 halves. And there's also 3 halves to infinity. And for each of these intervals, this rational expression is going to have the same sign throughout the entire interval. The sign could flip from interval to interval, but within a single interval, the expression is all going to have the same sign. So really, we can just choose some test points within these intervals and figure out whether the expression is positive or negative on the intervals. And then using that knowledge, we'll find our solution. So first of all, why don't we set up the top row of our sign table? So that's the intervals and breakpoints here. So there's negative infinity to negative 3 interval, followed by a breakpoint of negative 3, and then interval of negative 3, 3 halves, and then breakpoint of 3 halves, and then our last interval of 3 halves to infinity. Okay, so let's take care of our breakpoints first. Negative 3, what did that cause in the function? Well, that was when the denominator was 0. So that's when the expression is going to be undefined. Let's just abbreviate that with undefined. Okay, and then how about 3 halves? That was actually a 0 of the expression because that's when the numerator is 0. So that's when the expression is 0. Okay, now let's look at our intervals. Let's choose some test points. How about a test point of, say, like negative 4 for this leftmost interval? When we plug in negative 4 into 2x minus 3, that's 2 times negative 4, which is negative 8, then minus 3, negative 11. So just put down that to negative. And then negative 4 plus 3 is negative 1, so negative. And negative divided by a negative is a positive. So our expression is going to be positive all throughout this interval, negative infinity to negative 3. Now let's choose a test value in the next interval. Negative 3 to 3 halves. How about 0? That seems like the easiest choice there. So plug 0 into 2x minus 3, you just get minus 3, which is negative. Plug it into x plus 3, you just get 3, which is positive. And then negative divided by positive is negative. And lastly, the interval 3 halves to infinity. How about a test point of 2? And we plug that into the first 2x minus 3, we get 4 minus 3, which is 1, so positive, and 2 plus 3, it's 5, which is also positive. So positive divided by positive is a positive. Okay, so we wanted to solve where this expression is less than or equal to 0, and we know that it's positive on this interval, undefined at negative 3, negative on that interval, 0 at 3 halves, and positive on 3 halves infinity. So let's just circle which matches up with less than or equal to 0. That's not positive, not undefined, but negative is less than or equal to 0. Good. And 0 is less than or equal to 0. So these are good. And then again, positive, nope, not what we want. Okay, so these negative and 0 parts correspond to this interval -3, 3/2, and that endpoint of 3/2. So putting all that together, that's just going to be the interval -3 parenthesis to 3/2 bracket, because we're including that 3/2. So x has to be an element of that interval in order to satisfy this rational inequality. And there we have it. We're done. Here's another example. Again, we want to solve this rational inequality, x squared minus 1 over x squared plus 1 times x minus 2 is strictly greater than 0 on the real numbers. And now this is a bit of a more complex inequality, and we've also got a strict inequality. No or equal then is allowed. Okay, so let's start off by factoring this inequality a little bit more. We see that the top can be factored a bit. X squared minus 1 is just x plus 1 times x minus 1. And then can we factor the denominator anymore? X squared plus 1, no, we can't factor anymore, so we'll just leave it. X squared plus 1 and x minus 2, and that is greater than 0. Again, we need to solve for where this expression is 0 or undefined. So why don't we let's find the roots first where it's 0. So roots happen when the numerator is equal to 0. So x plus 1 times x minus 1 equals 0. And for that to happen, we need either x plus 1 equals 0 or x minus 1 equals 0, which means x equals -1 or x equals 1. Okay, so those are the roots. Actually, why don't we label that as roots of numerator. And we also want to find the roots of the denominator. And those are the values which make the expression undefined, because the denominator goes to 0. So roots of denominator, we can find those by solving, set this denominator equal to 0. X squared plus 1 times x minus 2 equals 0. So either x squared plus 1 equals 0 or x minus 2 equals 0. So if x squared plus 1 equals 0, then x squared equals -1, x equals plus or minus root -1, but that's going to be an imaginary number, and we're just worried about on the real numbers, so we don't worry about that. No real roots to be found from this factor, but from x minus 2 equals 0, we've got x equals 2, that's a real root, so we consider that. Okay, so x equals 2, x equals 1, and x equals -1 were our roots of the numerator and denominator, where this expression is 0 or undefined. Let's go ahead and plot those on our number line. The leftmost of these is -1, and then we've got 1, so 0 in between, then 1, and then we've got 2 also. So here we go, 2. Let's partition our number line here. So this one is -infinity to -1, then we've got -1 to +1, and then +1 to +2, and then 2 to infinity. Let's also write these intervals and endpoints in the top row of the sign table. So first of all, -infinity, -1. Then we've got endpoint of -1. Then interval -1 to 1. And then endpoint of +1. Then interval of 1 to 2. And then endpoint of 2. And finally interval of 2 to infinity. Let's also fill out this leftmost column with the factors here. So there's x plus 1 in the numerator, also an x minus 1 in the numerator, then x squared plus 1 in the denominator, and x minus 2 in the denominator. And our full factored expression was x plus 1 times x minus 1 over x squared plus 1 times x minus 2. Great, so now let's go ahead and figure out what these intervals and breakpoints correspond to in the rational expression here. So -1, that was a root of the numerator, so that's going to cause this expression to go to 0. Likewise, +1 was also a root of the numerator, so that causes the expression to go to 0, and then 2 was a root of the denominator, so that causes the expression to be undefined. Now let's look at the intervals here and get some test values. So negative infinity to negative 1, how about a test value of negative 2? If we plug in negative 2 to this factor here, x plus 1, that's negative 2 plus 1, which is negative 1, so negative. Then negative 2 minus 1 is also negative. Negative 2 squared is 4, then plus 1 is 5, so that's positive. And then negative 2 minus 2, negative 4, negative. Okay, so in the actual expression here, we've got a negative times a negative divided by a positive times a negative. So really we've just got an odd number of negative signs here, and the expression is going to come out negative because of that. On to the next interval, negative 1 to 1. How about a test point of 0? That's the easiest one. So 0 plus 1, that's positive. 0 minus 1 is negative. 0 squared plus 1, positive. 0 minus 2, negative. And even number of negatives here, so the expression is going to be positive because those negatives will cancel out. Test point in 1, 2. Ooh, that's a tougher one. How about 1.5? Just split it right in the middle. 1.5, well 1.5 plus 1 is positive. 1.5 minus 1 is just 0.5, which is also positive. 1.5 squared plus 1, well positive plus positive is a positive. And 1.5 minus 2 is negative 0.5, so negative. And then we've got a single negative sign, so that's going to stay in our expression, doesn't cancel out with any other negative signs, and expression is just negative. And finally, our last interval here, let's choose a test point of 3 in that interval. 3 plus 1 is positive, 3 minus 1 is positive, 3 squared plus 1 is positive, and 3 minus 2 is positive, and everything's positive, no negative sign, so our expression is going to come out positive. Great, we're almost there. Now let's just look back to the original problem statement. We wanted to find where the expression is greater than 0, strictly greater than 0. So negative is not going to work, 0 is not going to work because strictly greater than. Positive will work, so that's good. 0, nope, won't work. Negative won't work. Undefined, not going to work either, but positive, again, will work. And those positives correspond to these intervals, negative 1, 1, and 2, infinity. The solution then is just the union of these two intervals. X is an element of negative 1, 1, union 2, infinity. And there we have it, we're done. In these exercises, the right-hand side was always 0. In the future, though, we'll also learn how to deal with cases where the right-hand side is a polynomial or rational function itself.